Hello everyone, welcome to my YouTube channel. In part 5 of MD simulation series, I will be showing you the different steps which are involved in molecular dynamics simulation. So let's start from the beginning. The first step in MD simulation is preparation of the input. Input means setting up the initial structure which we are going to simulate. So this could be a protein ligand complex, a DNA molecule, a lipid bilayer, or other biomolecule. Okay. So suppose you want to determine the 3D structure of a novel protein for which no crystallographic structure is available. So you can do that by generating an initial 3D structure using AI tools like AlphaFold or other AI tools, and simply by providing the protein sequence. So once this 3D structure has been generated, you can simulate that structure until it stabilizes, and it will give you a stable 3D structure for your further computational work. Similarly, protein structure can also be obtained from homology modeling, and this structure can be simulated to improve the structural quality of that homology model protein. Okay. Sometimes the crystallographic structure of a protein contain missing residues. Okay. So when these residues are added using different modeling software like PyMol or Discovery Studio, okay, so the overall structure of the protein may change after addition of these missing residues. So it's important to simulate the protein for a certain period of time to allow it to stabilize. And after simulation, we get a refined structure or 3D structure which we can use for our further computational work. Okay. It's also important for drug discovery, because for drug discovery, molecular docking experiments are often used, and the base or top pose from docking can be combined with the target protein to form a complex. That means protein ligand complex. And after running molecular dynamic simulation of the complex, we can observe whether the complex remains stable or not. So through MD simulation, we check whether the protein ligand complex is stable or not. We can also use a crystallographic structure directly from the protein data bank for our simulation. Okay, but make sure that the input molecule only contain the protein ligand or the biomolecules of interest. That means the other elements such as ions, water molecule should be removed. So the input molecule should be cleaned, and after cleaning, that means removing the unwanted elements, water, you have to save this input molecule in PDB format, that means in protein data bank format. Then it will act as input molecule. So these are the inputs. You can also simulate lipid bilayer. Okay, sometimes the transmembrane protein or integral membrane protein, they remain embedded in the plasma membrane. So we have to simulate the protein along with the lipid bilayer. That kind of simulation is very computationally demanding. The second step in molecular dynamics simulation is box generation. That means in this step, we create an isolated system. That's why we generate a box surrounding our input molecule. Okay. And then we solvate this box. That means we fill this box with water molecule to create or mimic an aqueous environment. And for that, we use different kind of water model like SPC, SPCE, tip 3P, and tip 4P. And each of these model has its own advantage and disadvantage. Like in case of SPC or simple point charge model, it is the most simple and computationally efficient model, but it less accurate. Okay, so SPC is the simple point charge extended, is an improved version of SPC model. We also have T3P or 3-point charge water model. It's widely used, well tested, and compatible with many force fields. So therefore, it provides a good balance between the accuracy and computational speed. But it also has its own limitation, like it's unable to reproduce the water dielectric constant and few structural properties. Okay, so T4P or 4-point charge model is more accurate than T3P for properties like density and melting point of ice. Okay, but it's more computationally intensive and may not be compatible with some force field. So each of these model has its own advantage and disadvantage, and these models are about reproducing the aqueous environment more accurately and efficiently. And we choose this water model depending on the need of our simulation. So our box is now filled with water molecule, but the net charge of this system may not be neutral. Okay, so the system may be positively charged or negatively charged. Now we have to neutralize this system. Okay, and we can neutralize this system by adding positively charged or negatively charged ions like sodium or chloride, okay, to make the system neutral. So next step is adding ion. So we can add sodium ion, potassium ion or chloride ion to make the system neutral. So next step, you can see we have added ions. So now our system is completely neutral. Now the step 5, that means energy minimization. So in energy minimization step in MD simulation is used to remove any unfavorable contact or steric clashes in the initial structure. That means sometimes the atoms, few atoms are positioned too closely, and it creates an unnatural strained or excited state of the input molecules. Therefore, we need to minimize or relax the input molecule, and therefore this minimization step relaxes this input molecule by adjusting the atomic position and help the input molecule to reach a low energy conformation. And this step is very essential before running the MD simulation. Okay, otherwise the input molecule may distort or the system may collapse, just similar to a bursting of a bubble. Okay, the whole system may collapse. And for energy minimization, we use the steepest descent algorithm or method. Okay. The step 6 in MD simulation is equilibration. Actually, it's two steps. Okay, this equilibration is done in NVT and NPT ensemble. That means through two steps. And now what is equilibration? The water molecules, ions which are present surrounding these input molecules. Okay, so these water or ions, they are allowed to move, allowed to settle down surrounding these input molecules, because during NVT ensemble we try to achieve our target temperature, that means 300 Kelvin usually. So a thermostat algorithm is used in NVT ensemble, and the system is gradually heated to achieve the target temperature. That's why the water molecules and ions start moving. But during this ensemble, but during this equilibration, we usually restrict the movement of this input molecule which is present at the center. We only allow to move the water molecules and ions. During NPT ensemble also, the system is temperature of the system is maintained to 300 Kelvin, and also the pressure of the system is maintained to 1 bar or 1 atom. So during these two equilibration steps, we keep a positional restraint. That means we restrain or we inhibit the movement of this main input molecule. Okay, this is known as positional restraint. But we allow the movement of water molecules and ions so that they can settle down, they can adjust themselves surrounding the input molecule. Okay, if you directly run the MD simulation, then the system may collapse. That's why first through NVT and then NPT ensemble. Finally, the simulation run is performed in NPT ensemble. That means when the both temperature and pressure are fixed, then we run the NPT our production run in NPT ensemble, and we remove this positional restraint from the central input molecule. And when we run this M2 simulation, the whole system looks like, I am showing you how it looks like. So this is the system, ions, water molecules, everything is moving, simulation is running. Okay, so these are the general steps which are followed in different molecular dynamics simulation software. And that's all for the theoretical concept about the molecular dynamics simulation. And next tutorial, I will introduce you with the GROMAX molecular dynamic simulation software, and I will explain the different kinds of files and formats which are involved in GROMAX software. Okay.